So the next speaker is Patrick Bahr, who's going to try to show us how to use a high-order abstract syntax to turn trees into graphs.
Oh, there we go. All right. Yes, thank you very much. So this is joint work together with Bahr and Hutton. And so what we set out to do in this functional Perl is to improve on one particular aspect of the compilers that we get out of compiler calculation, making a bit more realistic. So to start out with, let me show you a bit about what I mean by compiler calculation. So the situation is this, right? You have given a description of a language, here a very simple one, right? So a simple expression language with integers and addition operation. Sort of the syntax is given as an algebraic data type, and the semantics is given by an interpreter, essentially, right here, evaluating expression to integers. And so what we want to do is, we want to get out of this a compiler, right? Derive a compiler by some kind of mechanical process. And not only that, we also want to get some kind of assurance that the compiler is correct. So we also want to have a proof of specification of the correctness of the compiler. And calculation can achieve this, right? So, it turns out what you can do is you can simply start proving the specification without you even having the compiler here on the right-hand side. And as you do the proof, right, you do this equational reasoning to complete the proof, you discover the compiler, right? The compiler definition falls out of the equational reasoning, right? And so let me show you a more concrete example. And to make it a bit more interesting, let me add conditionals, if-then-else expressions here. So we also extend the semantics, of course, and then we give the compiler specification. That's the actual specification we would give. This is for a stack machine, so we actually put something here, the result of evaluating E on top of the stack. That's what you expect. And then we go ahead and try to prove it. And as we do it, we discover the compiler in the end. And not only the compiler, but also two other things. Right? So the target language code here also falls out, as well as its semantics in the form of a stack machine here, the exec function, which tells us how code is executed on the stack. Right? And also importantly, the compiler itself is defined in continuation passing style. So in addition to the expression here, it also takes this code argument that is the code that we insert after we have produced the code for the expression. And this will become important for the actual calculation. Now, I'm actually not going to show you exactly how this calculation works out. I'm just going to show you the result, and we have a look at that. So let's assume we went through this process, and what we get out is something like this. We get a target language, we get the compiler that produces this target language, we get a stack machine, and also a proof of the correctness of the specification. Let's move that aside for the moment, these last two things, and let's focus on the target language and the compiler, right? And also the target language itself is sort of written in this continuation passing style. So each instruction comes with a code continuation, right? So for example, push says, well, push some integer on the stack, and after that, continue with this code that is given here. Similar for the add instruction. But it also means that if you have a branching instruction like the jump if zero, conditional jump here, this has to have two continuation, right? One for the two possible outcomes of this check. And this also has ramification for the compiler. As you can see here, when we compile an if expression over here, what we get out is this, where we duplicate the code continuation C here, because we want to continue in both branches of the conditional, right? So this is what you get out of this calculation. Let me show this an example to make this a bit more explicit, right? See, it's a very simple expression, and it compiles to nicely linear code here on the right. Push 1, push 3, add, halt, what we would expect. Here we have a conditional, and also again what we would expect, we have here the jump if 0, branching instruction, and then we have the two branches left and right. So in general, this code will be tree-shaped, sort of matching the branching behavior. But let's extend this example by adding a +4 here in the end, right? We add this +4, and if we look at what this results in the code here on the right, all of a sudden the code corresponding to this +4 is duplicated, right? It appears on both sides of the both branches of the conditional jump, right? So this is not what we would expect for a realistic compiler. So what we rather want is a compiler that produces sort of graph-shaped code, right? That instead of having this duplicated, has some kind of jumping from here over here, right? So that it rather looks something like this. So a compiler that produces some kind of graph structure. So that's the goal for this talk. How do we get there? Right? How do we calculate a graph-based compiler like this? We need some kind of specification that tells us how this compiler should behave. Okay. So on the left-hand side, we have the graph-based compiler that we want to have, and on the right, we have the tree-based compiler producing tree-shaped code, right? And the specification is rather simple. We want that the graph-shaped code on the left here simply unravels to the tree-shaped code that the original compiler, the bad compiler, will produce, right? So it's a fairly simple specification here that we get out. It looks like this, right? So compiling for the graph and then unraveling it is the same as the old compiler. But remember, the specification we actually want is the one that uses these code continuations. So this compiler that, in addition to the expression to be compiled, also takes a continuation. And here we also need to apply this unraveling. So we have this unraveling on both sides. So that's the one we're going for. Okay? So now we have our specification. Now we can go to this picture. It looks very similar to the very first slide I've shown you. Right? But now on the left-hand side, the stuff we got is the tree-based compiler, right? And what we want to get out by calculation is the thing on the right, the graph-based compiler. And we do the same dance again. We also want the proof of that. We have the specification that we want to have a proof for, and how do we achieve this? Well, we prove again the specification, and as we do this proof by equational reasoning, we get the definition of the graph-based compiler. Right, so the same technique applies here. But of course, in order to do this, we need some nice equational reasoning principles for our graphs. So how do we do this? So we need to find a good representation for these graphs so that we can do equational reasoning about them. So let's have a look how this can look like. So I'll show you this on an example. Right here on top, this is the tree-based code that we've seen for the example before. We have our 4 instructions. And this is how the code looks like for our graph-based representation. Right? This uses parametric version of higher order abstract syntax. And what this means in practice is that now our code type takes this argument here, this type, abstract type of labels as an argument. So this is the type of labels that we can jump to in our code. Right? For example, here, the jump instruction, the conditional jump, takes as a first argument this label type. So that's the label we want to jump to if the condition is fulfilled. If we find something, if we find a 0 on top of the stack. And then otherwise we continue with the code continuation here. And in addition to that, we also need 2 further instructions. So we need a unconditional jump that simply just jumps to a label that is given there. And we need this the pseudo instruction that labels code. Right? So it says it takes this code here and labels it with a fresh label, L, say, and then passes this label on to this first argument, which is the function that takes a label as an argument, right? And then this code here can use this label to jump to that label and thereby to this piece of code. So that allows us to do forward jumps, which will be just enough for this little example. So let's go with this representation. Okay, so now we have everything in place to start calculating, right? So let's do that. So this is our specification here on the right. And what we're going to do is we're simply going to prove this by induction on the structure of E, our expression language. So how does this work? So we start with the add case, actually. I'm going to skip the trivial case of just integers. And what we're going to do is we're going to start on the left-hand side of the equation. So here, instantiating E with add x, y. And then we're going to work our way to the right-hand side. So step by step, using equational reasoning, right? And of course, we don't know quite yet what the right-hand side looked like, right? Because we don't have the graph-based compiler. So what we're going to do instead, we're going to target some kind of code, C prime, right? And then we can simply make the proof go through by fiat, by just saying, well, these two things are equal by definition. In other words, we have just found the definition of our compiler for the case of add, by simply making these two equal for the case of the expression being add x and y. So this is the whole trick of the compiler calculation approach. And this also works here. So let's have a look at how this works for this example. So we start on the left-hand side for addition, and the first step is just applying the definition of our old compiler, the tree-based compiler, right? So we compile it by first producing the code for x, then y, inserting add instruction, then continuing with c. It's easy enough. And now the goal is to turn this whole expression purple, right? So we want to have the whole thing to be purpled, to have something, an unraveling of some code. And the first step is just applying the definition of unraveling. I haven't given it to you yet, but this is the relevant part of the definition for the add instruction, right? And that just pushes out the unraveling brackets one more step. And then we continue doing that. And for the next step, we simply apply the induction hypothesis that does exactly that, moving the brackets further out. So here's the induction hypothesis for y, and then we also do it for x. And then we're done, right? So now we have this expression in the form that we wanted to, and we can simply read off the definition of our compiler, the graph-based compiler. Of course, now looking at it, this calculation, it looks exceedingly easy because all the steps that you see here are syntax directed, right? And that is because there's no branching going on, right? There's just addition, so there's nothing interesting going on. So it's just a warm-up exercise for now. So let's look at a more interesting example, namely the one for the if-then-else. I need a bit more space. And this is how it's going to look. So I'll just give it to you in one swift go. And it looks like a lot. But if you look closer, most of the steps, the one highlighted in green here, they're entirely mechanical, right? In the same way that the ones on the previous slide were mechanical. They're just applying definition of the original compiler, unraveling, and induction hypothesis. Again, just to move out these unraveling brackets to the outside. There's only two interesting steps here. These are the remaining ones. And they are basically goal-directed. We have a certain goal in mind. And the first one is this one here. Here we have two occurrences of the continuations, right, C, that causes code duplication in the compiler. And we want to avoid this. And how do we avoid this? Well, we abstract over it. We introduce a lambda abstraction that introduces a variable, and then we use that variable instead of that code directly, and we simply pass the code continuation as an argument. It's just it's just beta expansion. And similarly here, remember our jump instruction, conditional jump instruction, we want to have this take a label as a first argument, right? The label that we can jump to, not some piece of code as it's given here. So how we do this is, again, by abstracting over this, introducing a fresh variable L prime that we then use there instead, and then pass the code that we found here as an argument instead. Again, this is just beta expansion, right? And with a particular goal in mind. And that's it. This is the full calculation, and we can simply read off the definition of our compiler for the conditional case. This is our full compiler now for this language. The first two cases, of course, are rather boring. Let's focus on the second one for the conditional. It's a bit tricky to read this kind of higher order abstract syntax definition. So here's a different way of different notation for this to make it more readable. So first we produce the code for x, then we do a conditional jump to L prime if it produces 0. So we go to the else branch, the code for z. Otherwise we fall through to y, and then in both cases we jump to the end, to our continuation. Right? So that's exactly what we would expect. So if we illustrate this as a graph, we get this nice diamond shape that we would expect from our compiler. All right, so that's all I have time to show you, but there's more on the paper. So in particular, we also show in the paper how this extends to, well, cyclic code, right? If you want to actually compile while loops, and it works in a similar way. You start out with building a calculating compiler that produces trees, and for loops, these will be infinite trees, right? So this compiler will actually produce infinite trees. Very unrealistic. But then you do the same trick doing the calculation for graphs using the unraveling, and the compiler that you get out for that is the one that you would expect, that has a backward jump to the beginning of the while loop, right? And so the same trick applies there, and we get the compiler that we expect. There's also active formalization of all the calculations in the paper. Also some more calculations that are not in the paper. For example, we calculate a compiler for the lambda calculus and for a language with expressions. So if you're interested in that, have a look at that code. And I'll stop here. Thank you.
Hi, Pedro from Type Theory for All. Just to make sure that I understood correctly, so this last part where you have the AGDA formalization, were you also able to produce the compilers from your proof? Or is that just something, yes?
Yeah, you get this compiler that produces this, the higher order abstract syntax.
From the proofs. You got it for free from the proofs.
Yeah,
you do the proof first.
You just read it off, right? You do the proofs, right? You leave in your active formalization. You sort of leave the compiler definition empty,
right?
Right, and then you do the proof, and then you can just read off the definition, just copy paste it into your compiler, and that finishes the proofs.
That is pretty cool. And you don't have any trouble getting the induction hypothesis and any of that, because I would
trouble with what?
The induction hypothesis. I would expect that the induction hypothesis would look weird since you don't have the actual definitions. You don't have that?
That works. The induction hypothesis works just fine. It gets a bit tricky once you go to loops, right? Because then you have to do co-induction. To do that properly in AGDA is a bit fiddly. But so to get around that, we use step indexing just to make our lives easier.
Very good. Thank you so much.
Hi, I'm Cesar Andrić from MPISP. I really like your representation of graphs. I did not understand if the labels you have, they have to be statically allocated, or you can generate new ones while looking at the code.
Right. In a sense, they are not really generated, right? They're just using this higher order abstract representation. In principle, you could take these higher order abstract syntax trees and then generate concrete labels, right? By having a monad that generates fresh labels, right? And then passing that onto this function that takes this label as an argument, and then actually producing linear code with actual labels, like 1, 2, 3, and so on. But the code that you produce here is entirely abstract, right? So it's just functions. It's just using the meta language to have variable binders, essentially.
Hi, Pedro Vasconcelos from the University of Porto. So can I just ask you a question? The choice of the abstract syntax, the higher abstract syntax, is crucial. And could you highlight sort of you picked the right choice for the labels and then it worked out? But I think it actually was the other way around, right? It was the fact that you wanted that kind of sharing that led to the introduction of the label constructor with that particular form, right?
Right. I mean, it's entirely, so here I just showed it on an example, right? But it's entirely generic, right? You can think of, you have some kind of a functor that essentially defines the syntax, both in the tree form and in the graph form, right? Where you just instantiate it with a particular kind of syntax functor that gives you both the tree form and the graph form. So, but yeah, this choice is taken so that each instruction has at most one continuation, and all other code things are actually these kind of labels in the right place. Yeah.
Okay, thanks.
Okay, let's thank the speaker.